Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so today we're very pleased to have Professor Peter Stevenhagen here visiting from University of Leiden, where he's chair of the math department. And we're especially pleased to have had two of Peter's students also here, Rainier Broker and Marco Streng, who was an intern last fall. Peter is an expert on many aspects of algebraic number theory. He has written about Hilbert's 12th problem and has produced a collection of surveys in number theory, which will be of great value to the community, I'm sure. So today he's going to talk about constructing abelian surfaces with a given number of points. Thanks, Peter.
Thank you, Kristin. I'm happy to be with Microsoft, first time, so thanks for the invitation. And this talk is actually part of a set of two talks, since later this afternoon Everett Howe, who will be separately announced, I suppose, will also give a talk on a similar topic. So I'm supposed to set the stage for the things he will be saying at the same time as telling about the result, which is sort of the main thing in this talk. So we'll be looking at some kind of inverse problem to the point counting. So point counting means we will be working with varieties defined over finite fields. So all the time I will be working with finite fields f. I'm not specifying their order, it will be a finite field. Most of the time later on it will just be the prime field fp. And given a variety over a finite field, so if v over f is a variety, and usually when I say variety I mean something like smooth projective variety, so described by algebraic equations, smooth projective variety, then such a thing will have a number of points. It's living in projective space, so what you can do for all these v's, you can count the number of points, so that's the point counting map, point counting, and then you get a non-negative integer, so v will be sent to its set of points defined over the finite field f. That's the set of points, and it has a cardinality, which I will briefly refer to just as the order of the variety over that finite field. So if I simply say order of the variety, I mean its number of points over the finite field f. So this is point counting, and the problems I will be looking at, and Everett will look at as well this afternoon, is some kind of inverse to this. Namely, first of all, you can ask, given a variety, how do you efficiently count its number of points? So efficiency will of course be a point, since all these problems will be finite. I mean, given the finite field, if your space has finite dimensions, only finitely many points, and you can simply count how many points are there. So actually finding an algorithm is never a problem, but doing it efficiently, as we will see, is much harder. So the inverse problem, which we will be looking at, so can we go back? That's sort of the central topic this afternoon. Can we produce varieties having a specific number of points? And usually if you want to go back, so that's sort of an explicit construction map. Yeah, the question is, given an integer n, non-negative integer, positive usually, the question is, can you find a variety having that many points? And usually you want more conditions on the variety. So for the inverse map, usually we won't be working with all varieties, but we will specify, well, say type x, additional conditions. So you should think of x as referring to, for instance, x additional conditions. So for instance, you might specify the dimension of your variety, say I want curves or surfaces or whatever, fixed dimension. Otherwise, usually the problem becomes too easy, since any number, of course, if you have complete freedom, is easy to realize as a point set of some kind of curve. If you want to, already for curves, it's sort of easy, fixed dimension or if I go for curves, then specific genus. And in fact, we won't do the full generality. Actually today we'll mostly be speaking on genus 2, curves of genus 2, and their associated Jacobians, which are Abelian surfaces, occurring in the title of my talk. And as I said, the whole problem is doing things efficiently. So we want efficient algorithms. And efficient has two meanings. It sort of has a practical meaning, sort of that if I give you a number n, that you can sort of in a short time actually use a computer and find a solution to the problem. So it means practical. It also has a theoretical meaning of polynomial time. And I won't take a very strict polynomial time computer science meaning in the sense that if it's heuristic polynomial time, we're usually just as happy. So we won't often insist on proving that a thing is polynomial time for a reason that I will explain. But if I can sort of explain why it should be polynomial time and it behaves fine in practice, then for our purposes that will be good enough today. Okay, so this is the general setting, and as I said already, usually in going back you want to specify which category of varieties you're looking at. And dimension is the first obvious thing. So if you start from the beginning, you would say, look at curves. Can you produce curves over finite fields having so and so many points? And first of all, it will of course depend on the cardinality of a finite field. So usually if Q is the dimension, if the number is the cardinality of your finite field and the dimension of your variety is D, then the point sets will be of order roughly something like Q to the D. And in practice, if you want to solve this problem for all n, as we will, that means that we'll almost always be restricting to prime fields, since there's very many primes among the set of all positive integers. But if you look at prime powers, that's a very thin subset, and usually you won't realize too many n's using f's of true prime power cardinality. So most of the time, for those people who don't like arbitrary finite fields, most of the time f will in fact be a prime field, fp. Okay, so let's look at our problem. In the case of curves, well, you can specify the complexity of a smooth projective curve by saying what the genus is going to be. And the genus is a non-negative integer. For genus 0, you're looking at conics. And for conics, there isn't much going on. They tend to have p plus 1 points that just look like p1s if they have points at all. So the first interesting case, and that's a very important case, first interesting case for us, which will also be the motivating example to use in all genus 2 constructions, interesting case where you look at curves of genus 1. So that basically means we're looking at elliptic curves. So that's the elliptic curve construction problem, elliptic curves. Efficient, if I say polynomial time, then you see that you have to bound the runtime of the algorithm you're going to give in terms of the length of the input. Well, the input, in the case of the reverse arrow here, you're just giving an integer. So the size of the input is just log n. And how much bits does it take to specify the output? Well, usually if you have a specific type X kind of variety, you're just writing down a number of equations. So for elliptic curves, the typical equation, if you choose your model in the standard Weierstrass way, for instance, then an elliptic curve for most cardinalities looks like this, where A and B are in your finite field. So you see that what it takes to specify an elliptic curve is just two coefficients, two elements A and B from your finite field F. So the output size is, well, two elements from F, and to specify an element from F, you need log cardinality of F bits. So for the prime field, your output size is something like log P. So let me just input size log n, output size something like log P. And since curves over Fp have about P points, I'll be more precise later on, this is roughly the same thing as log n. So small input, small output, and theoretically there's no restriction in the sense that it should be possible to find an algorithm, polynomial time in log n, that gives you an elliptic curve having n points. Okay. There's one important thing in going back for this arrow, that is the role of the finite field in the question. Since you can fix your finite field, so there's two versions of the question, two different versions, I should say. Namely, you can sort of fix your field from the beginning, and then you have a fixed finite field, and you can ask, given an integer n, can you produce, in this case, an elliptic curve having n points of order n over that finite field f. So for fixed f, so that means given n, you have to produce the appropriate elliptic curve over f. Or you can say, well, the input is only n, and I allow you freedom of choice in the finite field f. So allow choice of f as part of the output. So that means that you have much more freedom. You can select your favorite field fp over which you're going to construct your elliptic curve. So clearly this is the easier problem of the two. And the results I will be describing, they occur in the thesis of Renier Breuker, is basically that if you fix your field f, so this is 1 and this is 2, in this elliptic case I will explain why in 1 it's really hard. As far as we know, it's exponentially hard, meaning that the best algorithms that we can think of are just exponential time. And in the second case, if you allow freedom of the choice of your finite field f, then it's not quite polynomial time, but if n is provided in factored form, so that means that you get a factorization of n, factored form. Since, as you know, factoring n is something we don't know how to do in time polynomial in n. It's a hard problem, but if the input is given in factored form, then 2 is polynomial time. Well, basically for all n, let me just say for almost all n, and this almost all has a meaning that I will make precise a little bit later on. So that's the kind of result that you should think of. And of course, this afternoon, the main topic is if you replace elliptic curves by curves of genus 2, then in fact there will be two problems. There's my Abelian surface problem, and there is the true genus 2 curve problem that Everett will speak on, and we will discuss results for both of these problems separately. As we will see, these problems are in fact rather different. Okay, so for just in the elliptic case, so an elliptic curve, just before I actually provide the solution, let me say what is going to happen in genus 2. For elliptic curve, constructing the thing is just writing down this Weierstrass equation. So corresponding to y squared equals x cubed plus ax plus b, there is this standard picture. And the reason that elliptic curves are in fact very popular is that in that case, if you compute an elliptic curve and you take its set of points, EF is in fact a group. And as soon as you have a group, you have all kinds of cryptographic primitives like the discrete logarithm problem that makes elliptic curves in this particular case very popular. So in that case, you also have a sort of a strong reason to be willing to construct groups in that case for which the order is of some nice kind. For instance, prime order is something you would like for discrete logs. So then it also has rather than just being a pure mathematical question, it also has a cryptographic reason for being interesting. And this being a group, that is something that becomes a little bit different if you go for a higher genus. This being a group is caused by the fact that for elliptic curves, E can in fact be identified with its Jacobian. And the Jacobian is a thing that you can produce for any curve. That's always going to be a group. And in this case, it's the same thing. The Jacobian is a group that you can make out of a curve. If the group of points, the set of points on a curve is not naturally a group, you can look at the group it generates, just a free abelian group generated by the points. That's called the divisor group. So that's div of E. And that's a huge group, which is much bigger than the group of points that you have here. If you mod out by principal divisors, so principal divisors are gotten by looking at functions in your curve, principal divisors on E, and you mod out by that subgroup, and you look at the degree 0 part, you get this definition. This is a group, by definition, when you create it, and in general, the group of the set of points maps into this group. And for an elliptic curve, it's in fact a bijection, since to a point you can associate the divisor class of thing that you denote by p minus 0. The point 0 is the projective point that always doesn't occur on the affine picture. That's the point infinity of the elliptic curve. That's what you take as the unit point, the 0 point for the addition. And with that definition, you see that there's a bijection between the point, the set of points of an elliptic curve and the points of its Jacobian. And in fact, it's an isomorphism of group schemes, so it's true if you leave out the base field altogether. For genus 2, so this is the genus 1 case, you get two problems, and these two problems are exactly the topics of this talk and the next talk. So if your C is a curve of genus 2, you also have a map. Well, first of all, there's a similar model. Here you have a Weierstrass model. Genus 2 curves are also hyperelliptic. They can be written in the form y square equals some polynomial. So they look like y square equals f of x. And now you take the degree of f, which can be 3 or 4 in these elliptic models. It becomes 5 or 6. In the genus 2 case, take separable polynomials, that's a detail, but usually they look like this, so the picture is a bit more complicated, so you have more eggs up. That's a genus 2 curve. And its set of points doesn't form a group, but you still have exactly the same thing. You can map C using the point at infinity, which is again lacking in the picture. There's O of C, the unique point at infinity. This is a degree 5 example, then there's a unique point. You can map C into J, the Jacobian of the curve C, in exactly the same way. You can map a point on your curve to its divisor class P minus O. But in that case, it's not going to be an isomorphism of group schemes. C is not a group scheme at all. It will just embed the set of points in this group in this way. And this is the group, so from a cryptographic point of view, people tend to be interested in the Jacobian rather than in the curve itself. So this is the dimension is exactly the genus of the curve, so in this case it's a two-dimensional abelian variety, it's an abelian surface. And just like the points on the elliptic curve look like P minus O, with P ranging over the points of your elliptic curve, you can specify points on the Jacobian by taking sums of 2 points, P1 plus P2 minus twice the point at infinity. That's a degree 0 divisor, and these elements represent things on the Jacobian. As you see, it takes now 2 points. It's a two-dimensional thing, unlike the case of an elliptic curve where it's something one-dimensional. It's just the curve itself. So my general problem in genus 2 sort of splits in two different problems. Namely, you can specify an integer n and ask for a genus 2 curve having exactly n points. That's the direct analog of the elliptic question, where you ask for an elliptic curve having exactly n points over some finite field. Or you can say, well, I want to do cryptography, I want to have a group, let's look at the Jacobian, and then the question becomes, given n, can you produce a genus 2 curve for which the Jacobian has exactly n points over a finite field which will usually then be fp again. So now we have, let me erase this, two different questions. So question one, given n, find, in fact, as I said, there's two questions. This is hard, so one is already too hard for elliptic curves, so we don't expect to be able to do it for genus 2 either, which is only more complicated. So one we will sort of leave out. From now on, if I say realize n as an order, I do allow you the choice of the finite field in such a way that you can adapt it to your needs. So the second version of the problem is the thing we'll be looking at in the rest of this talk, and that will also be the approach Everett will be taking. So given n, rather than say find C, I should say find a finite field, find f, and C over f of genus 2 such that, actually to be more efficient, I should say that the problem, both problems start like this, but there's version 1. You can ask that the number of points of C defined over f becomes equal to n, so that's curves of order n, or second one, if the Jacobian is denoted by j, you can ask for a curve that has the property that if you take a Jacobian and you count points that you get a group of order n. And I will look at this problem in my talk, so this is for now. And this problem is the problem that Everett will talk on. And in fact, Everett will have a positive result and I will have a negative result. But it's part of the same problem, and in fact that's something I should have said right in the beginning. This all arises, this is all joint work with Kristin, Everett, and myself. This is our San Diego project that is still unfinished, but it's getting close to some kind of answer. And the answer that we will give today is that for curves, you can do it in many cases, and do it means that you find an efficient algorithm, again under the same conditions in the elliptic case. In fact, the solution will be related to the elliptic case, and I will also show that for Jacobians, so the cryptographic case if you want, the answer is that we cannot do it efficiently, at least not using the methods that we have been using in the elliptic case, the CM methods that I will explain in a moment. So, how do we attack the problem in the elliptic case, and in which way can we extend that attack to the genus 2 case? So in the elliptic case, first of all I should of course observe that the problem being finite, there should be an algorithm. So if you don't have to be efficient, how would you just do it if say p is small or n is very small? Yeah, so there's always a naive algorithm which is just to proceed by trial and error. Yeah? If you have an elliptic curve over a finite field, which will be fp for practical purposes, since there's just many primes and not many prime powers, if you count the number of points of the elliptic curve over a finite field, then you will find an element in the Hasse interval around p. It will be in the interval p plus 1 minus twice square root p, p plus 1 plus twice square root p. And conversely, any element in this Hasse interval arises at the order of some elliptic curve over fp. So the naive algorithm is just try random curves, so that means given n, you pick a prime such that n lies in this interval. So if I call this Hasse interval around p hp, so you could say pick p such that n is in the Hasse interval around p. You can phrase it completely symmetrically. If you define hp for any integer p like this, n being in hp is exactly the same thing as saying that p is in the Hasse interval around n. Yeah?
Do we know distribution of primes will always be such a P.
That's a problem. So you see that if you want to prove that around any integer there will be a prime which is no further than twice the square root from that integer n, you have to prove theorems on prime gaps. And as it happens, these theorems are currently too weak to prove that such a prime really exists.
Don't you have gap cases where the two h's are not exactly the... just the plus one should make the two conditions differently. N in Hasse P and P in Hasse N, there's a plus one there, and of course the square root can be a little bit bigger in one than the other. So
this is exactly the same thing. Yeah. This is square root P minus 1 square. And this is square root P plus 1 square. And if you write down the inequalities, and you get exactly the same condition. We'll see in a moment why it is symmetric in P and M. So this is the practical problem, that you may not be able to find a prime which is sufficiently close to n, in theory. But as I said, I erased it already, I think, we will be practical. And from a practical point of view, you know, that's the prime number theorem, that around n, about 1 in log n integers is going to be a prime number. So that means in this interval there will be loads of prime numbers. And in practice, if you pick random integers, you will find a prime, well, after time log n, so to speak. So this being my practical approach, I'm happy if I have a big interval, if I can pick random integers, they will be prime with probability 1 over log n. So that's an expected runtime, which is not a proven runtime. And as I say, proving it is just way too hard. You have to bound the gaps between prime numbers, which people cannot do. But that's something in analytic number theory we won't be bothered by too much. So if you do this, you pick your P such that it's in the Hasse around n, and then what you do, look at random elliptic curves E over Fp. Count the number of points on that elliptic curve. That is something, count, that can be done efficiently, so use Schooff's algorithm. So in that case, at least point counting is something we can do efficiently. You just count until you hit n. And if you look at the distribution of orders over these intervals, and you make sure that your prime is not too far from n, it's pretty much equal distributed. It's not exactly the case, it's more like a circular thing, but it means that the expected runtime, you just have an interval of length multiple of square root p, and you have some n, integer n you want to hit, and that happens with probability 1 over square root p. So the runtime in that case is O. Well, square root p and square root n are of course the same thing, yeah, in the sense that p and n have the same order of magnitude as you see here. So p is roughly equal to n. That's as it happens with curves. You see that the runtime becomes O n to the 1/2 plus a little bit to do your Schooff counting. So that's a square root n algorithm, meaning that it's certainly exponential, and for large values of n it won't work. But at least it is a solution. It's a probabilistic algorithm. And let me compare it to a deterministic algorithm that will be used. And that requires a little bit of background on elliptic curves. Namely, if you want to count points that are defined over Fp, then you have the map from the elliptic curve to itself if E is defined over Fp. You have the map on points which maps, well, for the affine point, just raises everything to the power p. That's the Frobenius. It's a map from E to itself. It's an endomorphism with respect to group law, E being defined over Fp. And we're looking for points that have coordinates in Fp, meaning that in fact it's being fixed by this Frobenius. So the set of points E over Fp is fixed points of Frobenius, and you can also phrase it a little bit more algebraically, namely Frobenius is an endomorphism, so you look at the ring of endomorphisms of this elliptic curve. Inside there is just multiplication by integers. Any point you can just double it or triple it, so you get z as a subring, and you also have this Frobenius thing. inside the endomorphism ring. And the FP rational points, they just form the kernel of what people call 1 minus Frobenius. Things that are mapped to 0 by 1 minus Frobenius, just saying that the Frobenius of the point is just the point itself. And the way people approach all point counting for elliptic curves is by actually studying this endomorphism ring. That's also the case for Schoof's algorithm. And what you need to know then is that the Frobenius, it satisfies a quadratic equation. It's the characteristic polynomial of its action on the Tate module if you want, but it just, the only thing you need to know is that the polynomial looks like this. It's a quadratic polynomial. And that just means that this subring, so if pi is a 0 of this imaginary quadratic polynomial, so the discriminant will be negative, so delta, which is t squared minus 4p, will be a negative integer, and this ring generated by z and Frobenius is just, well, how you want to write it. It's an imaginary quadratic ring. It looks like z delta plus square root delta over 2. It's the quadratic order of discriminant delta. And knowing what is Frobenius, what it generates, is exactly what you need to know, since if you want to look at the kernel of 1 minus Frobenius, then you look at, so usually the Frobenius, which is in here, will correspond to an element in this quadratic order that people call pi. That's the associated Wien number. It's the 0 of this polynomial, so that's t plus square root delta over 2. And what we're looking at is just the kernel of multiplication by 1 minus pi, and the theory tells you that the number of elements in this kernel, that's the order of the elliptic curve over fp, is what you get as the norm of this 1 minus Frobenius, the element 1 minus pi, and that's just saying it's 1 minus pi times its complex conjugate. And pi bar is p, as you see. Here's the product of the two roots of the quadratic polynomial, so you'll find p plus 1 minus pi plus pi bar, and pi plus pi bar, that's the integer t, called the trace of Frobenius, the trace of the quadratic integer pi, and as you see, t squared is no more than 4p, so this deviation from p plus 1 is at most twice the square root of p, and that's exactly what you find in the Hasse bounds for the elliptic curve. Okay, so point counting just amounts to analyzing what Frobenius does, and it's the same thing, so to speak, as computing the element pi in the endomorphism ring as an imaginary quadratic element. And the reason that everything is symmetric in p and n, to come back to your question, is that the way p and n arise is that p is pi bar, and if n is the order, so if n is the order of the elliptic curve, then you see that n is 1 minus pi times 1 minus pi bar, so that means that n can be written as nu times nu bar, where pi plus nu equals 1. So that's completely symmetric in p and n. Here I'm just writing that nu is in fact 1 minus pi, and that's the identity. Okay, so much for point counting. So that just means that what you want to do is analyze the Frobenius element, and constructing an elliptic curve with a given number of points just amounts to writing down an elliptic curve for which the Frobenius is some prescribed element pi, giving rise to the right equations. So to construct an elliptic curve with a given number of points, what do you need to do? You have to construct an elliptic curve for which you can say something on the associated Wien number pi. In fact, these are the equations that you try and solve in the quadratic order O delta, where everything is taking place. Let me see how much detail I want to give on this. Basically, the method that is used to produce elliptic curves deterministically, that's called complex multiplication, CM. And what it does is that rather than writing down the elliptic curve in characteristic P right away over Fp, it creates the elliptic curve with the right endomorphism ring over the complex numbers, finds it to be algebraic, and reduces it mod P. So it's a big detour. So find E with the endomorphism ring of E equal to the right thing O delta, since given your input, so if you have an N and a P, and you want to realize an elliptic curve having N points over Fp, you see from this equation that N equals P plus 1 minus T. So that gives you the desired trace of Frobenius, and then you see that delta, which is t squared minus 4p, is the order in which everything is going to happen. So then this is the ring O delta in which you need to find your pi and nu. I'm not going to specify in much detail how that happens, but given this ring, you can write down a finite list of elliptic curves for which the endomorphism ring is actually equal to O delta. It corresponds, by the complex analytic theory, to the ideal classes of this order. That's because over the complex numbers you can make elliptic curves as C modulo a lattice, and these lattices are exactly the ideal classes for the order O delta. So what you do is you write down the J invariance of the associated elliptic curves. That's just an expression in terms of the A's and B's that gives you the isomorphism class of the elliptic curves. So you find them over C, that is their J invariance. These are complex numbers, but in fact they're algebraic, since it turns out that if you take the polynomial, which has all these J invariants of elliptic curves as its roots, all J invariants of elliptic curves E up to isomorphism, complex analytic isomorphism, for which the endomorphism ring is isomorphic to O delta, then you get only finitely many isomorphism classes corresponding to the class group here. It's called the class polynomial, the Hilbert class polynomial of the order O delta. Let me call it H delta. It will be a polynomial in Zx. That's the algebraic property of the whole thing. These complex numbers are in fact algebraic numbers, they're algebraic integers. And once you're here, you can reduce everything mod p, pick a root, that's going to be your J invariant over Fp, and you simply write down the elliptic curves. So reduce mod p, and take E over Fp, maybe E bar if you want, such that its J invariant is a root of this polynomial H delta mod P. It will always be in the prime field in Fp, and you've got your elliptic curve. It's a very nice deterministic algorithm, and the only problem is that you have to compute this polynomial, and it's a huge polynomial. Its degree is about square root delta. Its coefficients are of size square root delta. This takes time just to compute the thing. It takes time big O of delta. In fact, absolute value, delta being negative. And the problem is, if you now look at what your delta was, t is something, can be anything, small, but at most 2 square root p. T squared minus 4p is something of order p, which means of order n. And that means that this very nice algorithm has runtime order something like big O of n. And the conclusion is that this mathematically better algorithm behaves awful in practice, since just the naive thing was only square root n. And this better algorithm is just n itself. So that's not going to work unless you do something tricky, and that's what occurs in Reniers' thesis. Namely, you reverse your point of view a little bit, rather than picking your p close to n and just take any t that happens to come out. The reason it doesn't work is that delta will be too large. You just reverse your whole thing. You say, let's delta be small. So you take your order as small as possible in such a way that you can find a prime such that these equations hold. And what does that mean? You just take the smallest delta for which you can factor n into two elements in O delta. So that's Reniers' approach, Breukers' theorem if you want, approach, whatever. Approach, find the minimal O delta such that you can factor your n as nu times nu bar in O delta. That means you have to factor your integer in this quadratic order, not just in ideals but into principal ideals, and the norm of 1 minus nu. 1 minus nu is the thing that I call pi here. That's the thing that has to give rise to p. That should be the prime number. It's a prime number p. And if you approach it this way and you analyze it, you find that actually this delta is going to be of order no more than the square of the logarithm. So minimal delta is expected to be big O of the square of log n. So it's going to be polynomial time. Since this delta determines the runtime, it's going to be big O of delta. If delta is something which is the power of log n, you're fine. And if I say expected, I mean that there's a heuristic analysis of exactly of the kind 1 out of every log n numbers around n is prime. That kind of arguments gives rise to this theorem. Okay, so here's the approach that works in genus 1. And the question is, can you generalize this somehow to genus 2 for these two examples? So that means that you have to generalize the elliptic theory to the genus 2 case. And what I wrote down here is also true for genus 2 curves, only the Frobenius lives in a ring which is a little bit bigger. It's exactly the same kind of argument. You look at Frobenius, it's an endomorphism of the Jacobian, and it's characteristic polynomial, so genus 2. You also have point counting on the curve, and its Jacobian is the same thing basically as determining the value number pi that is the root of the characteristic polynomial of Frobenius. So determining the characteristic polynomial of Frobenius. Yeah?
What is the difference from Akin-Moran approach to really small discriminant approach?
You mean in primality proving?
It's Akin-Moran approach, just the complex analytic method to generate the Hilbert class model. Just the fact that you use, once you determine the delta, then you use what he's calling the Akin-Moran approach to actually compute the Hilbert class model.
Oh yeah, that's a very classical algorithm. So this computing H delta from delta, that is the classical complex multiplication algorithm that was also used by Akin-Moran. That is basically 19th century. Yeah? Yeah, so, but it's only efficient if delta is really small. Since the runtime is O delta. So that means you can only do it if your delta is going to be yeah. So the reason that, so the method is not new in the sense that it's just complex multiplication, but the way you approach it is not by selecting, picking your prime and doing it for n over that p. That's the hard problem. A given order for a fixed field fp, you sort of select your p as it comes out of this analysis of a small O delta. So you have to factor n. That's the reason why you need factors n. Then you need principal ideals. That's something you have to check efficiently again. And then this is sort of a random number, and as soon as it is going to be prime, you have found your P. That's the way the algorithm works. And the hope is, of course, you can do the same thing in genus 2. So that means that this theory now tells you that rather than looking at a quadratic polynomial that gives rise to everything, there's a degree 4 polynomial. So the polynomial now looks like x to the 4 minus ax cubed, something like this. It is somewhat symmetric, like this, p squared. And once you have this characteristic polynomial Frobenius, you know everything about what there is to know about c and j, namely then the order of c over fp becomes p plus 1 minus a, which is the trace of Frobenius, just as before. And the order of the Jacobian, which is then a surface over fp, its order is in fact what you get if you plug in, if this polynomial is f, you compute f of 1, which is the norm of, well, the norm, you have to be a little bit careful, basically of 1 minus pi in a generic situation where pi is the root of this polynomial. So generically this will be irreducible. Then q of pi is a field of degree 4. It's a CM field, meaning it has a unique real quadratic subfield, k plus. There's q, these are quadratic extensions. Use q pi plus pi bar. And from the norm of 1 minus p, which is an element, well, something close to p squared, these a's and b's are again something very bounded, just like here the t, the trace of Frobenius in this polynomial was at most twice square root p. Similarly, here you have that a is no more than 4 times square root p, and b is something close to 2p, no more than, I think, 4p away from it. So the order, if you plug in x equal 1, it's roughly p squared, and here is the deviation. So this is of order p squared, order of magnitude. That's because this is a curve and this is a surface. So that means both Everett and for my problem we need to find suitable Wien numbers giving rise to things having the right number of points, either on the curve or on the Jacobian. So either you want this to be equal to n or you want this to be equal to n. And I will now focus on the case where you want to fix the number of points on your Jacobian, so you want 1 minus pi to have norm equal to n. And then I will show that if you do that by complex multiplication, which is the only algorithm we can hope to sort of generalize this Breuker approach, that it will be intrinsically exponential. So, and I will explain why. So, CM approach to realizing n as the order of the Jacobian over some prime field Fp. Well, what do you need to know? All the things that generalize the, if you want, Aitken-Morin CM construction. Now you have to do it for genus 2, and the theory, well, if you attended a talk by Marco Streng, I think you heard more about it, but it takes a talk by itself. So let me just say that rather than computing this Hilbert class polynomial, in genus 2 there are in fact 3 polynomials. The moduli space is 3-dimensional, and these polynomials are called Igusa class polynomials. So I'm not going to explain it in any detail. So rather than finding an elliptic curve with a given endomorphism ring, the theory that finds you an elliptic curve, and now a curve of genus 2, C of genus 2, such that the endomorphism ring of the Jacobian is whatever it should be, some order O, and O is now an order in a quartic field. So it's the, if you want, the ring of integers or an order in this K. Can be done in a similar way. And the runtime will also be exponentially discriminant. In the case of the classical Aitken-Morin it's really big O of D. It's sort of sharp. The size of the output is what it takes to compute the whole stuff. Here it's not as sharp. Your discriminant, well, I guess Everett will tell you more about discriminants, since you see that there's a quadratic subfield, so there's in fact two discriminants. There is the discriminant of k plus, and you can write delta k as the delta of this k plus times something else that you can call delta minus. And the runtime, it will be exponential in delta. Marco's strength proved that it can be bounded by some power of delta k. I think he proves 7/2. That's a highly non-trivial theorem. That's Marco's strength result. It's big O of this is an upper bound, and it is at least, since now in the case of the Broker result, you prove that something is efficient. You just need an upper bound on how difficult something is. If you want to show that something is really difficult, you need a lower bound on the runtime. And a lower bound of the runtime, if you look at the similar way, then similar means that rather than writing down the Hilbert class polynomial, you need a thing called the Igusa class polynomial. So there's in fact 3 of them, but each of them is associated to the ring of integers of the number field k, OK, and these Igusa class polynomials, their degree equals delta minus. And that's the delta minus that you find here. That's a factor of the discriminant. But since delta minus is in fact a multiple, maybe not n, some other multiple, m, times the delta of k plus, you see that delta minus is, so to speak, the bigger factor of delta k, so it's at least the square root. So it's at least the degree of the Igusa polynomial, Igusa class polynomial, which is, roughly speaking, delta minus to the 1/2, and that's at least delta k to the 1/4. So the runtime is bounded by delta k to the 7/2, and there's also a lower bound, which is at least the 4th root of delta k.
Do you mean on the left say that the degree is the minus class number, and that's about the square root of delta minus? Or?
Yeah, and this was a shortcut just to say that it's roughly equal to this delta minus.
But on the far left you have
The far left. Oh, this. It is the class number, and the class number is roughly equal to delta minus. The square root of delta minus, yeah. Sorry. Sorry, that? So you do yeah, so in the Atki-Morin case, you have to list the ideal classes of your quadratic order, right?
Just like in the previous case, what is a similar way? Analogous to genus.
Yeah, similar way means that you have points in the complex upper half space. It's now a two-dimensional thing where you evaluate certain transcendental functions like the J function, and these give you the roots of this Igusa class polynomial. So there's a complex approximation, and the polynomial in the end is going to be algebraic. It has rational coefficients. So you approximate it as complex numbers, and you do it so well that you recognize the fractions. It's pretty non-trivial since these are huge polynomials, but it can be done. And well, the non-triviality sort of is visible from the 7/2. It takes a lot of time to do this, also in practice. And it's also much more recent in the sense that people now start doing this. There's databases. David Cole has a huge website which lists these Igusa class polynomials. Whereas the classical ones already, you find them in Weber more than 100 years ago. Okay, so there's a lower bound for the CM algorithm, and the question I want to answer in the last few minutes is why, unlike the elliptic case, won't it be possible to do it with a discriminant which is bounded by some power of log n? That's what you would like to get a polynomial time, or at least heuristically polynomial time algorithm. And the reason that it doesn't happen is basically because there's not sufficiently many of these k's. And another way to say it is that for the curve case, p and n are of the same size. for the Jacobian, you see that p squared is close to n, so p can be no more than square root n. And that's going to kill you in the following way. So, question is, which k can we use? Are there small k's to give rise to a given n? So, to realize all n up to some bound by CM method, the CM method, meaning that you find the number pi in such a way that the norm of 1 minus pi is n. How many k's will we need? Well, any k, that's sort of step one, any k has no more well, how many y numbers pi can you find such that the norm of 1 minus pi is going to be n and n is below b? Well, then you need primes of norm no more than square root b. And by the prime number theorem for the number field, there will be no more than up to a log than square root b. So has no more than b to the 1/2, well, there's a log b if you want, y numbers pi with norm of 1 minus pi below b. So that means that one field k only gives rise to this many y numbers at most, and that's an upper bound. So to do all the n's up to b, you will need very many. So to realize all this b up to n, you see that we'll need at least square root b times log b different number fields, different CM fields k. And the question is, if you have that many different CM fields k, how large will their discriminants be? So that means that, just like for quadratic fields, you want to know how many there are for which the discriminant is bounded. Well, in the quadratic case, it's fairly easy. That's sort of a linear thing, since if you just take number fields, the deltas are essentially the square-free numbers. And the square-free numbers up to some bound grows linearly in B. Something similar holds for CM fields, but it's much harder to prove. Let me do that here. That's a theorem of Henri Cohen and two other people from Bordeaux, Diaz et Diaz and Olivier, from 2000 something, 2, somewhere around there. If you count the number of CM fields k, so k, quartic CM, of discriminant no more than some bound b, maybe we should call it x, it's not the same b as there. If you count those, then asymptotically this behaves like a constant, an explicit constant that you can compute times x. So just like in the quadratic case, there is linear growth. If you bound the discriminant by x, you get a multiple of x, that many quartic number fields. So it's the same kind of result for quadratic fields. It's easy. Then you just count basically square-free numbers, and there's something involving pi's at zeta 2 times x. The same theorem holds here. And that means that if you take at least so many fields, then the discriminant has to grow also like square root b. So you will need k with discriminant at least square root b. Let's just forget about the log, it's not so interesting. And if you now look at the runtime, if you do CM for such a k, which you will need if you want to do all the n's up to b, you see that the runtime for such k, the runtime will be at least, well, it was somewhere here, where was the runtime? Oh, I erased it. Well, the runtime, let me repeat it, the runtime was at least the discriminant delta k to the 1/4. So that means that in this case you get at least b to the 1/8. So that means that it will be exponential in terms of the bound. So if you want to do all n's up to a bound, then you get at least some positive power of n. This is a somewhat weak result, since you see that there's various steps where I've been a little bit sloppy. In fact, since the runtime, the lower bound is just given in terms of delta minus, it would be better to prove a theorem that replaces delta k by delta minus. And if you do that, then at least Cohen says that you get something, if you do this, then you get times log x. So bounding delta minus gives something which is a little bit more than linear, but only a logarithmic factor. And if you do that here, then you conclude that the beta, the b to the 1/8, is in fact at least b to the 1/4. So it's even more exponential than the first version. And even that is sort of bad in the sense that the lower bound is really a lower bound. It only uses the degree of the Igusa class polynomial, and in practice, Kristin has done many computations with Igusa class polynomials. They're huge, so the size, in fact, should be much bigger than the square root of delta minus, but it's hard to prove upper bounds for these coefficients. Just like in the case of the Hilbert class polynomials, for all we know, they might be sparse. Many coefficients could be 0. That never happens, but proving it is very difficult for all I know. Okay, so this is an example where a problem is just too hard to do it by CM methods. So negative result, but there will be a second talk on a positive result. Thank you. No questions? Well, yeah?
Has there been any challenge done, for instance, this is root 1915, so how many curves are there with 1915 points compared to 1916?
You mean for elliptic curves or genus 2 curves, or?
Are there some?
Well, in the elliptic case, well, you see, for elliptic curves, the order of the curve is in fact the norm of an element. So you would expect that if your number is highly composite, there are potentially more elements that would have that norm. If you want prime order, then it has to be a prime element in your quadratic order. So I would guess that prime order is relatively, there are not as many, so 1915 is not a prime number, so it's hard to compare it to 1916 from that point of view. Maybe 1917 is prime. Neither is prime, exactly. But I would guess that it depends on the smoothness of the number.
I would kind of expect heuristically that if you're looking at elliptic curves, you would get roughly n elliptic curves over some field that have n points. I think.
It depends on what you fix, right? If you, you can ask all these questions. You can ask them in various ways. You want to fix a field and then ask how many curves are there over that field with so many points, or will you fix your... Yeah? And for genus 2 it's rather different, so that the number of points on the curve is not a norm, right? So that is a bit structureless, and I think it should make a big difference. I mean, traces, do you have properties?
Maybe this is really for the next talk, but is the number of points on the curve rather than the Jacobian any used in crypto?
No, it's not a group. So it's not yet used in crypto, I should say. It's very safe against the discrete logarithm attacks. It's not even a group. There is no discrete logarithm. But it also is. Yeah, it is not. Yeah, so cryptographically speaking, this number of points on the curve is maybe, well, that's your topic. You should sort of, I shouldn't say it's useless. It's a beautiful question. If you want, it's the more natural one, right? Elliptic curves, genus 2 curves. It's only because of crypto that you want to look at Jacobians. Can I say?
Yeah.
Okay.
More questions? Well, we're going to go and have some coffee in the cafe area with Peter before Everett's talk. So let's thank Peter again.